Welcome here at GameDuell. Willkommen bei GameDuell. So as this talk tonight will be in English, I will also give you some introductory notes and hints in English. GameDuell is for those who do not know, is one of the leading companies in the fields of social and casual online games, and we exist since 2003. We have 80 million players worldwide, and we are one of the leading companies, particularly in the Western markets, Europe and North America. And on our web platform we have 70 games online. We have around 5 million games played each day on the web platform and 500 million page impressions per month. So this is quite a high load of traffic we handle here. And our community and games platform has also much content for the players. We try to involve them actively into our games. All this is brought to life by our team of 200 people here at GameDuell. We quite actively expand into the fields of social and mobile games too. We have 13 social games running already and 8 mobile games. So this is a segment or sector which we want to expand in the future, and we are actively looking for people also to join our team. So we want to expand the team by 100 more team members until the end of the year. You see behind you here, there's a construction site already. So we are actively preparing the offices already. So this is a thing for the future. But now some formal and organizatory notes. Could you just switch to the next slide, please? So, yeah, we get there. Okay, so we're a bit behind schedule, but this is the rough agenda for today. We want to keep the tech talk for today for around 1 hour approximately, and then we will have time for questions and answers. Don't know if you want to have questions also during the speech. That's possible also. Okay, and then we have some snacks for you and drinks, of course. So that's for that. And if you want to have a smoke later on, we have a beautiful rooftop terrace. Just join this staircase over there at your right hand side. Restrooms are over there, just in this stairway. And we have prepared Wi-Fi for you if you want to blog or Twitter or whatever you want to do now. There's a Wi-Fi called GD TechTalk, which is the network and also the password for that. But now let's dive into technology. Yeah, GameDuell is hosting speeches of industry or technology pioneers since quite a few years, and we do that regularly under the name of TechTalk. And if you want to keep in touch with us about that, we have a TechTalk group on Zing. For those of you who are not registered there already, just join us there and we will keep you updated about future events in that regard. Okay, but now to our today's speaker, Jakob Engel from Technical University of Munich. He is researching about computer vision, about the autonomous navigation of flight devices using optical devices, optical cameras, onboard cameras to detect the environment and to map the environment in 3D. And this is his topic today. Last year he won the Siemens Award for his master thesis. So please give him a warm welcome, Jakob Engel.
Thanks for the introduction. I'm a PhD student at the Chair of Computer Vision at the Technical University in Munich. And so I'm coming from the research side. I'm going to talk about autonomous navigation of small-scale quadrocopters. I brought 2 of them with me. So this is one model we work with, it's the Per-Day Adrian. And then we also work with a slightly smaller version, which is this one. It can fly, it can carry a camera, and we're currently in the process of getting it to fly autonomously. So, First of all, motivation. Imagine you had a flying camera. What would you do with it? And I think it doesn't take you long to come up with cool ideas what you could do with a flying camera. Nowadays, lots of people want to take pictures of themselves, want to take pictures of themselves doing sports, skiing, biking, something like that. Often you can use a GoPro, for example. You can put it on your helmet and take a video of what's in front of you. But the problem is, the most important part, you yourself are not on the video because the camera is looking forward. So there are some methods to remedy that. People came up with the glorious idea to put the GoPro on a long stick, carry the stick around with them so they can carry it in front of them and take a video of themselves skiing. It's not an ideal solution. You might imagine that skiing with a long stick and holding in the hand is not as easy. And also you can only see powder on the image basically. So it would be really cool to have a possibility to have, for example, a small quadrocopter, maybe even of this size, with a small camera, which might not be high quality, which might not give you high quality videos, but it could give you a video of yourself skiing down without needing anybody else steering it, without needing like a full-scale quadrocopter taking videos or something like that. So here's another situation, biking. Again, GoPro attached to the bike, and you get a video out of it that looks like this. It's very shaky. You can see something, you can see the landscape, but again, you might want to see yourself as well. Third scenario, again, biking. Here, people are actually carrying around a stick with a GoPro on a bike. Here you can see this guy doing a BMX stunt, and down there standing a guy holding, again, a camera on a stick. So it seems to be a popular method, and there seems to be a lot of demand for taking videos or taking images from perspectives which you can't reach, where not like one person can go there and take the picture. Third scenario, kind of the extreme case, climbing, rock climbing. Here, often enough, it's actually completely impossible to take a picture for some human being because simply, well, the picture is taken out of the air, basically. So you have to fly to get there. You can get a full-scale quadrocopter with a camera on there. That's really, really expensive. You might be lucky and there might be another mountain, so you can like stand up with zoom objective and take a picture like that. But then again, the possibility to have like a device this big, which you can just throw in the air, which will circle around you once, take a video, then fly back, you can catch it, put it back in your pocket, and you get like a maybe low resolution, maybe bad quality, but you could get a picture of yourself hanging on the wall. Of course, there are other applications. One application would be to build three-dimensional reconstructions of buildings. So if you want to re-interior design a building, or if you're an architect, interior architect, it's really, really useful to have accurate, scaled plans of how the building looks like. Usually you don't have them anymore, especially for old buildings. These plans get lost. The building gets rebuilt and the plans don't get updated. So usually if like a big construction hall needs to be renovated, they send a team of architects in there and they measure everything, they take pictures and they draw plans of how it looks like right now so they can have an idea of what they need to do. The idea is basically you could take a camera, walk through the building, and automatically out of the video that's taken, make a three-dimensional reconstruction of the building. If the big building, a large building, maybe you want to have the reconstruction also from the outside, then again you need a quadrocopter to fly around because, well, you can't take a picture from the roof if you can't walk on the roof, at least not that easily. Bridge inspection, or in general, inspection tasks. I think in Germany every single bridge has to be inspected for structural integrity every second year. And the way that's done is they get a big crane to lift somebody below the bridge so that somebody can have a look at the bridge. It's kind of a big, seems kind of complicated. It is complicated, and again, it might be way easier to have a quadrocopter just fly below the bridge, maybe a bigger quadrocopter with better resolution, high resolution camera, which can take a picture. And then if you see, okay, there's something that needs to be done, then I can get the crane and go down there. Roof inspection, you might not want to walk on the roof, you might just want to fly above the roof. Search and rescue, avalanche or like crashed buildings. Often enough, the terrain afterwards is not safe for humans to enter. So here, for example, you have a church. I think this was a year ago in Italy. There was an earthquake and the church collapsed partly. And they had a big problem that it was really unstable. They didn't know it could crash completely anytime. So nobody could actually walk in there. But they still wanted to see how it looks like, what's going on in there. Like they had to go inside to get an idea of how stable it is, but they couldn't go inside because it was too dangerous. So they sent in this drone, the flying quadrocopter, sent it in. It's equipped with a Microsoft Kinect similar device, so a depth camera, and they sent this thing in, remote controlled by one of those guys who's piloting it with remote control, to take pictures. Again, really useful to do that. In this particular case, you're flying indoors, so just as a notion, if you're outside, it's easy to navigate because you have GPS. If you're inside, GPS usually doesn't work, so it gets a lot more complicated. One recent example I read, I think 1 or 2 months ago, the German Telecom is afraid of wire thieves. And people are stealing the telephone wires and selling it for copper, making a lot of money with it, and obviously the telecom doesn't want them to do that. So they get a quadrocopter, attach some kind of chemical artificial DNA marker, fly on top of the wire, apply this marker to the wire, and then it's marked, and hopefully nobody who steals it can sell it ever, because it's marked, and the vendor is going to recognize, okay, you stole this, you can't sell it. Again, currently this works by a pilot with remote control flying the quadrocopter up there, applying the marker, flying it down, putting it back in the car, driving a kilometer further, and doing the same thing all again. In conclusion, quadrocopters are great tools. You can do a lot of stuff with them, but they're difficult to control. They're really hard to control, and sometimes you might not have a person who can control them. Like in the sports scenario, you might not have a second person who could like stand on next to you and fly the quadrocopter while it's videotaping you. Maybe you need to react quickly, and there's nobody close by who can fly such a thing. So what we want is the possibility to give higher level control commands. So what I mean by autonomous flying in general is not necessarily to autonomously decide what to do, where to fly, and so on. It might just be to offer higher level commands to the user. So instead of having to use a remote control like this and to fly the quadrocopter around manually, which is not easy, trust me, and takes a lot of practice and so on, and if the quadrocopter flies outside of your line of sight, it's basically really, really hard to control it. Instead of this, you want to be able to maybe use your smartphone to give it a command like fly and take a video of myself from 3 meters away for the next 2 minutes, and after that land. Or show me, or you might have a computer, a laptop with you, with a live stream of a camera on the quadrocopter, and then as a construction worker on top of the bridge, tell it, okay, I want to have a close-up view of that part of the bridge, and then the quadrocopter is going to autonomously fly there and give you a good view of that part of the bridge. Or will the telecom thing just tell it to fly along the wire and apply the marker every 200 meters, let's say. So the idea of autonomous flying is, as I said, not necessarily completely autonomous, but to offer some kind of higher level control, some kind of higher level interface. Okay, where are we for today? Motivation. I hope you all got an idea what you can use a quadrocopter for. Now I'm going to say something more about who I am and what we do at the Chair of Computer Vision. Then I'm going to show some cool current state-of-the-art videos mainly of quadrocopter research. And then the most important point, I'm going to go into what I do and also tell you a little bit about how it works, how it's implemented, and the live demo is basically going to be exactly that. Okay. So, this is us at the Computer Vision Chair of the Technical University of Munich. Professor Daniel Kremers is my boss, basically. And most of this work is joint work with Jürgen Sturm and Christian Kell. So, us three, we are basically the quadrocopter guys. You can find open source code, so especially if you have an AR drone, if you have a laptop running Linux, everything I show in the live demo later today is open source. You can download it, you can install it, and you can fly your own AR drone with it, or you can tinker around with it, extend it, whatever you want. You can also find a couple of YouTube videos, publications, etc. So, what is computer vision? Computer vision basically is the art of getting information out of images or videos. So, if you look at it, as a human, if you see an image, you can get a lot of information out of it very quickly. You literally can see it. An image says more than 1,000 words. As a computer, or for a computer, an image basically is a bunch of colored pixels, and you can't do much with it. You can display it, you can maybe modify it, but really understanding what's going on, what's seen in the image, is a really difficult task. And computer science in general is not exactly known for being predictable. There have been a lot of famous mispredictions, and here's one concerning computer science. In 1966, Marvin Minsky at MIT asked his undergraduate student Gerald J. Sussman to spend the summer linking a camera to a computer and get it to describe what it saw. Well, now it's 50 years later, and we know that it's not as easy as that. It's absolutely not as easy as that. For example, Google image search, you can search for images, but when you search for an image of a tiger, for example, it's going to show you images of a tiger, but it's going to show you images that have the word tiger written next to it in text. It's not going to show you images that actually show a tiger. Well, it might be the same images, but Google can't, or at the moment, still doesn't really look at the image itself. It just looks at the surrounding text and classifies the image, or assumes that what's in the text around the image is probably going to have to do something with the image. Google is working fast, and many companies are working fast to change that, so there's lots of image recognition stuff. I mean, every single camera now can detect faces and stuff like that. There's a lot of progress being made, but still we are far, far away from getting the computer to be as smart as a human being, basically. So this is, in particular, what we do. We do 3D reconstruction using a Kinect. Kinect is a RGBD camera, so it's a camera that gives you not only the color of each pixel, but also the depth of each pixel. It's been launched by Microsoft 1.5 years ago, I think, and is used a lot for games, or it's meant for games, but it's been used in robotics and in research a lot. Especially because it gives you the depth for each pixel, which makes everything a lot easier. What we recently did is we developed an algorithm to easily scan in people. Everything that you need is a laptop, a Kinect, and a rotating chair, and then it takes 10 seconds. You can just sit on the chair, rotate the chair, rotate once around, and in real time it's going to give you a small model of yourself as a 3D mesh, which you can then send to Shapeways and have it printed. So this is me printed. We did it with the whole chair. We are still trying to decide who gets to be queen and who gets to be pawn in our chess game, but it's another topic. So that's really cool. You can do the same thing with objects, with buildings, with everything. And I think that in the future it has a lot of applications, because you simply can take an object and you can very quickly get a rough, it doesn't have to be very precise, but you can get a rough 3D object into the computer as mesh, colored with texture, and then you can use it, you can extend it as graphics design or whatever. Yeah, we are actually selling the software right now. So, second big part, what we are doing at our chair is image segmentation, trying to find out what is foreground, what is background, what is in the image, stuff like that. And my specialty, motion estimation, so I want to find out, given a camera, given the video of this camera which is moving in 3D space, how does it move, and how does the space look like it moves in? Okay, so let's get started with quadrocopters. Quadrocopters, the first successful quadrocopter flight, this one here, was in 1924. Can take off vertically, land vertically, but it was very hard to control. It was actually pretty much impossible to control. That's why 10 years later, the first helicopter was invented and took over, and since then, basically only helicopters have been built. Up until 2001, more or less. 2001, MEMS IMU sensors have been invented. Those are tiny little bits, tiny little parts, which are today in every cell phone, which measure accurately acceleration and rotation of itself. So basically when you have a smartphone, it knows when to turn the screen which way. That's basically because it has an IMU in there, and the IMU tells it which way it's facing. Same thing, Google Sky View uses this stuff. And they used to be pretty big, pretty heavy, inaccurate. They have been invented not in 2001, earlier, but since then there was a big breakthrough and people started realizing, okay, given these sensors which can give me the rotation of an object very accurately, very quickly, at a high frame rate, and which are very light and small and cheap, we can build cool quadrocopters. Because these sensors basically allow to keep the quadrocopter horizontal in the air. Basically, if the quadrocopter stands horizontal in the air, it's going to keep its position. If it stands like this, it's going to fly that way and so on. So basically, it steers by adjusting the motor speeds and adjusting its horizontal angle, and thereby it can steer. So if it points the wrong way, it can't fly, and that's why you need those sensors. And these are the platforms. Yes?
Why don't you use a single copter?
Why don't we use a single copter?
IMU and single copter would work as well, or is there a difference too far?
Well, one big difference, battery life is better on these ones. And I don't know, there's lots of arguments, so I mean, there's obviously you have toy single copters as well. So you can build them small. One big problem with them is they have this very complicated swash plate architecture, which is basically what it does is it adjusts the tilt angle of each rotor blade during the rotation. And this is always mechanical, it's very fragile, it's complicated to build, especially in small scale. On a quadrocopter, on the other hand, you don't need that. You can steer by simply making one motor faster than the other, and you can attach the propeller, you can just stick it on the motor. So you don't have this mechanical thing which breaks quickly, which is really fragile, and which actually in real world helicopters is the part that needs the most attention, basically. Second thing, safety. 4 small rotors are a lot less dangerous for people if the quadrocopter hits a person than one big rotor. So this one, the small one, for example, if it flies against somebody even without the hull, it's going to hurt a little bit, but nothing's going to happen. If you have like a bigger one with this kind of diameter of the rotor, then it's you can't fly close to people because, well, it gets dangerous. Did that answer your question more or less? Cool. Yeah, so that's why these quadrocopters got really famous. And once you attach a camera to them, you can do really cool stuff. This is just a random video I found on YouTube of a guy flying with a camera attached, and you can see that it does really cool stunts. What you can do in the extreme phase is you can get the video glasses with small screens inside. You can put them on, and then you can like fly in first-person view and do this kind of stuff while standing on the floor. I'm pretty sure it's not legal to fly around like that, but anyway, it's cool. But our goal is to do the same thing automatically. And the first way to do that, or many people do it by using motion capture systems, external motion capture systems. I'm pretty sure many of you have seen this kind of system before. It's basically, it has been developed and it's mainly used to get movements of actors into the computer, so you can apply these movements to animated figures in movies or in games or something like that. So basically it's a bunch of infrared cameras which track these infrared markers attached to the person and give you the pose, the position of each marker very accurately, very quickly, high accuracy and so on. And once you have this motion capture system and markers attached to a quadrocopter, you have the possibility to know the quadrocopter's position exactly. And then you can do really cool stuff. So this is from Grasp Lab in Pennsylvania. It's actually a couple of years old already. And they started doing really cool tricks with quadrocopters. You saw the flips, and now they can fly through very narrow slits, which are about as big as a quadrocopter. Even vertical slits. The interesting thing is here they fly through a slit the moment the quadrocopter passes through the slit, it's actually in a position where it can't hold itself. It's completely vertical, so it can't keep that position. But through the accumulated momentum, it can actually get through there and catch itself afterwards. So you can even fly from below through there. The thing is, this is only possible if you have the pose of the quadrocopter very accurately, very quickly, have external computers to calculate all the control signals. Yeah, can perch to a wall and take a break. They never really show it taking off again, because I think it's not possible, but it's still a cool thing. Like, you could fly into a room, stick to the ceiling, and then you have like I don't know, a surveillance cam which can fly into a room, surveil the room without actually somebody going there and attaching it. You can go even further, you can start doing constructions with quadrocopters. So this again, same lab. They use quadrocopters to build structures. And this is obviously in a lab environment, this is small, but it's a proof of concept. It's basically the idea that you can, as an architecture even, you have new possibilities, because you can build stuff made out of many small blocks with very few human interaction very quickly, and you can construct things that otherwise you couldn't build, basically. So currently this isn't used yet, but I think it will be used in future. And you can go even on, you can, instead of only having one quadrocopter doing the building, you can have multiple quadrocopters doing the building. So here they have 3, and they just pipeline the building. You have 3 quadrocopters, one picks up the thing, flies it there, the next one goes, picks the next block up, and so on. You can scale that to 10, 20 quadrocopters, whatever you want. Then, well, all computer scientists like to play, and this is from Zurich. They demonstrate how accurately you can control them by playing ping pong. And here you can see 2 quadrocopters playing ping pong with one another. I've been there, I've seen it, and it really works. So I just went in there, they showed it to me, and it's not like it works 1 in 10 times, it actually works each time, more or less. It's really cool. But again, controlled environment, you have these markers on the quadrocopters, you can't see them here, but you have those tracking cameras everywhere. So this only works in this cage. You can't do it in the real world. But it's pretty cool stuff. They also have like a net where they can throw balls and then catch balls with a net and stuff like that. And again, scalability. This is again the UPenn. They developed a small one, which is about this size, a little bit bigger. Again, attach markers to it, and you can just throw it in the air and it catches itself. So you just motor switch off, throw it in the air, it switches on and stabilizes itself and keeps flying. Can do flips. By the way, this one can do flips as well. And you can go up and take 2 of them, take 4 of them, take 8 of them. I think half a year ago they did like a Star Trek sign in the sky of, I think it was London, something like that. So they took 30 quadrocopters, attached lights to them, and flew like a rotating logo in the sky of the city. I think even like Disney World is interested in buying a bunch of those to replace the fireworks each night. So there's cool stuff you can do. Yeah. So this is the last video. Again, this is really cool because I've actually been there and I've done that. The idea is to use a Kinect to track the person, and then the person can steer the quadrocopter by just moving his hand. So you can see if the guy points upwards, the quadrocopters fly upwards, downwards, and so on. Raising the left hand does a flip, and yeah, it's a really, really cool feeling. I can tell you, just stand there, you hold your hand out, and you can fly around with the quadrocopter in space like this. It feels a little bit like Star Wars. Actually, it feels a lot like Star Wars. Anyway, so if any of you happens to be in Zurich, just go by and ask if you can get a demo. It's really cool. Okay, but what I'm working on and what this talk is mainly about is the question, can we do that with only onboard sensors? So it's really cool what you can do, but you can do it only. But if you can do it only in a lab, then it's good for videos, it's good for shows. But for example, I couldn't do it here because I would have to install 10 cameras before being able to do anything. So the question is, can we do that with only onboard sensors? And mainly what we use a sensor, what simply is the best sensor so far for doing that is optical cameras. So here you can see an optical camera attached to this little bugger. Here you can see our bigger research platform, which is Aztec Pelican, which is like 0.5 meter wide. Carries a complete computer on it, that's why it's so big. Stick a camera on there. You can also stick a Kinect camera on there, which makes things a lot more easy. And then try to navigate with that. Answer is yes, we can. It's possible, but it's really complicated. And currently, a lot of people are working on that, but the technology is developing. Back to the overview. Where are we? Next point up, our research. So I'm going to tell you what I actually did and what I will show you with the AR. First off, I'm going to say a little bit about the AR itself. Then I'm going to introduce the software framework we use for all the programming, which is ROS, Robot Operating System. And then I'm going to go into more details about how visual navigation works. How can I get the position of a moving camera out of the camera image? And then there's the live demo. So this is the Faraday drone, costs €300 on Amazon. So if you're missing a Christmas present or birthday present, this is actually a really cool idea for people aged 5 to 99. You use a smartphone as remote control. The AirDrone runs on wireless LAN, so it just sends the video and all the sensor information to your smartphone. The smartphone can display it, and then you can just tilt the smartphone around. So you can just like use your smartphone, fly forwards, backwards, left, right, so on. And you actually get the live video feed of the AirDrone on the screen. It has two cameras, one pointing forwards and one pointing downwards. The downwards camera is used on board to stabilize this AR drone. So this AR drone already has a lot of visual navigation methods built in. Basically, it tracks the movement on the floor and thereby can estimate its own velocity and stand still. So that's what makes it very easy to fly. The algorithm it uses is actually very similar to what's going on in an optical mouse. So an optical mouse does the same thing. It tracks the image of the desk below it with a red light, and has a really tiny camera, 16 times 16 pixels. Tracks how the mouse moves at I think up to 6,000 frames per second. So really high frequency, and that's how the mouse knows how you move it and works the optical mouse. And this AR drone does something roughly the same way to stay in one spot. It also has obviously the IMU and an ultrasound altimeter, which makes it really cool time. Okay, next point, the actual software framework we use. May I just ask, who of you has heard of ROS, Robot Operating System? Not many, okay. So robots tend to get more and more complex, and especially in the last decade. People have noticed that. Up to 8 years ago, there was no good framework. There was nothing that basically everybody had to do their own drivers, their own control structure, and everything. And here you have a famous example. This is Stanley. Stanley is an autonomously driving car from the University of Stanford, which won the DARPA Grand Challenge. I think driving 80 miles through some desert autonomously. Stanley won this challenge in 2005, and here you can see the control structure or the system layout of Stanley. It has a lot of sensors. Here you have like laser scanner interfaces, GPS, so on. Here you have low-level mapping stuff, road finder, laser mapper, vision mapper, and so on. Control structure, path planner, steering control, and so on. UI, emergency brake, some logging stuff. So it's a really huge system. They have tons of sensors. They have multiple computers in the back of the car which have to communicate, and at that point it became clear that, for example, if one laser scanner driver crashes, you still want the car to be able to brake or to steer. So basically, if something here goes wrong, you want this to be unaffected. Ideally, you want to have like a health monitor which notices, okay, laser scanner 3 doesn't work anymore. I can just shut down the driver, restart it without the rest of the system being affected. And that is basically how ROS was born. So the guys who built Stanley later went to Willow Garage in the United States and started building ROS, Robot Operating System, which is a middleware for robots. It offers drivers for lots of sensors, drivers for actuators, so joints, everything. It offers software management tools, communication tools, lots of libraries, a lot of stuff. It's mainly written in C++. It has a very good Python interface. It also has a Java and JavaScript wrapper, but they're not really used that much. Basically, it's mostly C++. In numbers, as I said, it was released 2007, so that's 6 years ago. By now, it's supported by over 90 robots, has over 175 software repositories and 3,500 software packages, which is a lot. So this is basically 2 new software packages a day over the last 6 years. And basic concept of ROS is very simple actually. You have nodes, which are basically processors. They can run on any computer. You have messages, broadcast messages, so you have message topics where one node can publish something and other nodes can listen and receive this something. And you have services, so one node can say, okay, I have a service, you can call me and I'm going to do something for you. And if you call it, it's going to do that. All communication between nodes runs over LAN, so the complete system can be distributed across different computers, even different hardware, which is very useful because if the laser scanner crashes and tears down the computer it's running on, then maybe you still want to have access to the emergency brake because it runs on a different computer. And this scales well. This is a really big example. This is the PR2 robot, also from Willow Garage, which is built completely on ROS. It's the kind of robot that researchers use to for example, get a robot make you pancakes in the morning, or to open your beer, or here I think it's just opening the fridge door. So it's the kind of robot that will maybe someday be able to assist humans in that kind of stuff, or like washing dishes, something like that, putting the table. That's like the famous tasks. Here you can see a couple of numbers: 2 arms, 7 degrees of freedom each, 7 cameras, 2 laser scanners, 2 8-core CPUs, 3 network switches. So there's a lot of hardware. It's actually really expensive as well. And just if you press the start button, it's going to start 73 nodes, have 328 message topics and 174 services which can be called. So that's just the basic sensory layout running. It doesn't do anything, it just stands around and offers you access to all it can do. This is the graph view of how the complete system looks like. Each circle is a node, each arrow is a message topic, which one node can subscribe to, the other node can send messages. This is a close-up, so this is a huge system. Some code, how can you use ROS? Very simple, this is just a simple publisher. So it's a C++ program which does nothing but initializes ROS. Then it advertises a message channel called chatter. So it tells ROS, hey, I'm gonna send some messages of type string on a channel called chatter, maybe later. And then it actually does send a message, and that's basically all it does. Very simple subscriber. The counterpart of that, again, process starts up, registers with ROS, subscribes to the channel chatter, and specifies a callback function. And whenever some other node sends some message on the topic chatter, this callback function is going to get called, and in this case just prints the message. Very simple, very simple layout, but it makes things a whole lot easier. Basically, a sensor can just be wrapped around a node which publishes messages. A camera is just a ROS node which publishes image messages on some topic. A robot joint might just be a rod which offers a service. Call me, and I'm going to set the joint to whichever position you want, and so on. And it's a simple idea, but it's taking foot very, very quickly, 6 years, and basically everybody is using it. I mean, that counts for something. Okay. That is ROS, and that is what I use, and the software I actually wrote it on Windows and then put it onto Linux and wrapped it into ROS, so you can use it in ROS. But now we're at the point where I come back to the original topic, that is how to navigate using a camera. And the central question in there is, where am I? So that's the question that's answered by the external tracking system. It tells you exactly where the robot is. But if you don't have an external tracking system, if you don't have GPS, you need some other way to answer this question. Simple solution would be dead reckoning. So you use the IMU, you get the acceleration out of the IMU, just integrate over the acceleration to get the speed, integrate over the speed to get the pose, and then you have a prediction of how your robot moves. That's basically the equivalent to walking around blindfolded. You can walk around, like I could probably from here reach the bar without my eyes, but that's it. Every single misjudgment I make on the way is going to add up, and after time my pose estimate is going to be really, really bad. So the error accumulates over time, and that's really bad. We really don't want that. So how does this look conceptually? Conceptually, here you have a robot driving in a circle, and the black dot is where it thinks it is, and the blue circle just shows its certainty. So the bigger the circle, the more uncertain it is about this pose. And you see it does the circle, and the uncertainty grows. How can we remedy that? How can we make it better? Well, we can use landmarks as reference. That's basically the idea. I have some reference point, stars, a church, I don't know, a spot on the floor, something. I see that, I can locate myself with respect to it, and using this observation I can remove this accumulated error over time. So that again is how it looked like, same situation. Uncertainty grows, and then you can see the landmark, the robot sees the landmark, uncertainty gets small, and then it grows again. That's the very basic concept of how can I navigate with a camera. I find points, I refine those points, and then I can take out this accumulated error over time. Even if you start with a wrong initial estimate, here, once you see the landmark, the pose gets corrected, and we're back on track. So that's the very basic concept on how to navigate with a camera. This is how it looks like in ROS. This is like a standard ROS display program. Here you can see I'm adding 2 image channels, AR image and USB image, and the TF display. Now the cameras need to get started. Here you can see the drone bottom view, here you can see the external view. And now the drone's just going to take off, fly around, observe these markers on the ground, and each time it sees the markers on the ground, you can see the recognition here. The uncertainty is going to get really small. So here it can see the marker, it knows exactly where it is. Now it flies out of line of sight of the marker, it doesn't know anymore where it is. And each time it can see the marker, it can make its own pose estimate a lot more certain. Again, fly a short circle, can't see anything here. Uncertainty grows and grows and grows and grows. Now it can see the marker and it knows again where it is. And that's the basic concept. But to do that, we need information about how the world looks like. We need to know where are landmarks and what are good landmarks. So that's the second big question. And these 2 questions together, what does the world look like and where am I in this world, are called the SLAM problem. It's like one of the fundamental problems in robotics has been around for decades. Simultaneous localization and mapping. So simultaneously build a map of the environment and locate yourself within this map in real time. Here you can see image from the quadrocopters. This is image from the camera, and you can see lots of colored dots. Each colored dot is a landmark. Each colored dot here corresponds to one red dot in this map, which is like the 3-dimensional position of the landmark. And by tracking these points, I can find out how the camera moves. So first of all, how do I get the map? For now, I assume I know how the camera moved. So I know the camera translation. I can see a point in one image. The camera moves a little bit, or the quadrocopter with the camera attached moves a little bit, sees the same point again. And by seeing how the point moved in the image and knowing how the camera moved, we can triangulate the depth of the point. That's basically the idea of stereo vision. That's why we humans have two eyes. We can see the point from two eyes at the same time and have 3D vision. If you only have one camera, you can still do that, but you have like to see the point, move, see the point again, and you get again 3D information. And you do that for a lot of points, and then you get a map. And ideally, you want to refine the position of these points over time to add more observations and get it more accurate. How does the tracking work? Well, again, for this step, assume the map is given. So assume I have a bunch of three-dimensional points in my map. First step, you need to refine those points in the image. So you have a bunch of map points, you find the locations in the image, and then you have lots of correspondences between a 2D position in the image and a 3D position in the world. And you use all these correspondences to find a good camera position. And I promise this is the only formula I put on the slides. Basically, we're working a lot with formulas, so I figured at least one formula I should put on there. This is done by minimizing the so-called reprojection error. The reprojection error is basically C is the camera position. I want to minimize over all possible C, all possible camera positions. And what I want to minimize is for each pair, for each correspondence between a point and the map and its found position in the image, I want the distance between this image position and the position I expect the point to be at, assuming camera pose C, that position should be as small as possible. So basically I choose the camera position such that I see the points in the image exactly there where I should see them, according to their position in the map. So here you have the observation to the image position. Here you have the pi function, which just takes the 3D point, rotates it into the camera coordinate system, projects it into the image, gives an image position where I expect the point to see to be. Take the difference, take the square root of the absolute distance, sum up over all pixel correspondences. That's my error function. I want to minimize this, sum of errors as small as possible, and then I get the ideal camera position. And from there it goes on. I mean, then you need to find out how to minimize this. That's not so easy. You have to compute derivatives, do some numeric stuff. But that's basically a major part of what we do. Yes?
How do you identify the same point from different angles? Because, I mean, a point looks different if I look from a different perspective.
Yes. In general, the assumption is that the point is on a flat surface. And then you can calculate, like the general assumption is that it's a texture point on a flat surface, and then you can calculate how it looks differently. But still, you're completely right, you can only find the same point from, let's say, 30 degrees different viewing angle, but that's why you have so many points. I mean, you have lots of points, and each point, maybe you can't see the point from, obviously from the opposite side, you can't see it probably at all. But you just have many, many points, and maybe some of them you can recognize again. But that's a different, difficult thing and a good question, because it's closely related to the second question: how do I choose good points? What are good points? Yeah.
One question: the SpaceX is a six-dimensional configuration space, or?
No, the C is six-dimensional camera position.
Yeah, but you optimize over D.
I optimize over C, which is the camera position, and the X, the observation, is 2D pixel coordinates. And the X map is just three-dimensional coordinates of the point in the world. So this is a two-dimensional vector.
The bold capital X, the space.
Ah.
Six-dimensional space.
No, that's the set of observation pairs. So that's just a set of point correspondences. Discrete set of points. So that's my 100 points which I have in the image and which I have in the map. Yeah.
Why do you try to find one idle position for the camera and not choose several ones?
How do you mean?
why do you try to find one idle position for the camera and not about 5 good ones?
Okay. Well, if I have 5 hypotheses, then I still don't know how to steer the quadrocopter. But the general idea is it's a video, so I have a very rough. I have the position of the previous frame, and the assumption is that the movement between 2 frames is small. So you have a good initialization, which makes it easy to find the correct minimum. But I mean, there is only one true position, so you want to find the true position.
So I didn't. No, I understand. Yeah.
Okay. But yeah, it's actually tricky to minimize this, and it's an error function. It has lots of local minima, so you might go wrong.
So you do this to find your correct position for every frame.
Yes.
This is one. Yeah.
Yes. So this is like you have an incoming new frame. You don't know the position of this frame. You find points in this new frame, match them to map points, and then find the position of this new frame. Yeah.
How do you distinguish between things that they are moving by themselves?
You don't. Basically. So obviously that's not all that's going on there. You also have lots of mechanisms that remove false points, that add new points, that do some afterwards optimization if the initial guess was wrong, and so on. The assumption is that the world doesn't move, and everything that moves, it's gonna get sorted out at some point. So it's a difficult question because yeah, you can't really know it, but there's some robust outlier function, so which basically says, okay, this point is absolutely very far away from where it should be, so it's probably an outlier, it's probably something that moved, or some weird reflection, something is wrong, so it's just going to ignore it.
And what happens when something appears in the middle, like, oh,
And visual tracking is going to get lost. If somebody occludes the camera, then there's nothing you can do. So that again, that's an important point. We're trying to get wide angle cameras, so wide field of view, and maybe 2 cameras looking in different directions. So that's another problem. Like if you're flying close to a white wall, you can't see anything. You can see a white wall, but that's not going to help you with navigating. So 2 cameras in opposite directions maybe is a good idea. Yeah. Okay. This is how it looks like in practice. You can see the colored dots here. You can see the map, and I think you might be able to see some red points, which are the map 3-dimensional points. And this is just a video for each frame. The points are found. You can see that the points roughly stay, or pretty accurately stay, at the same position in the world, so they kind of stick to the corresponding corner points. And the position of the camera is tracked here. That's the scale of the point. So, in order, like, you want to find points which you can re-identify afterwards, and that's basically points which correspond to corners in the image. So you need the image value to change in all directions, and some of those corners are very fine corners, very small corners, and some of those corners are very big corners. And that's basically what these points are to scale, like if it's a big corner or a small corner. Yeah?
Is it scale? You use some SIFT-like algorithm for recognition?
Well, you could use SIFT, but SIFT is very slow. And this doesn't use SIFT. This just does Lucas Canada tracking on the points. So you have a good initialization of where you expect it to be. You match some close possible matches, take the one that resembles the map point most, and then you do Lucas Canada optimization to find the exact position of that point. But other methods use SIFT or SURF, but they are slow. Yeah.
What do you do when the light changes? Do you have a model for light sources or something?
Again, the assumption is that the light doesn't change. In general, it's not too much of a problem. So, in fact, here we use to calculate the difference between template, or to calculate the difference between 2 points, we use the normalized cross correlation, which means that from both samples, the mean is subtracted. So if the brightness changes constantly, then it's not going to change anything on the error function. Then again, if you have highlights, if you have like some reflections, if you have, there's lots and lots of cases where this goes wrong, But then again, that's where you have where the throwing points out part comes in. Yeah.
I see many points, and I'm wondering, do we have better results if we have as many as possible, or is there a certain number where you say this is enough, so we try it out more and less, and if we have exactly, I don't know, 256, then we're done with it?
Well, in general, it gets more accurate the more points you have, obviously. But then again, for quadrocopter flying, maybe you don't need a millimeter accuracy, just like 10 centimeters might be enough. On the other hand, you don't know how many of those points are wrong. So especially the part that, like, if you only have 200 points and 50 are on a moving object, maybe everything goes wrong. The more points you have, the better it's going to be. So basically, more points, better. And actually, in practice, you have between 500 and 1,000 points. But again, that's different, depends on the algorithm. So there's different versions. By color?
Yeah.
Yes. Lots of people try to put color into the whole thing. Lots of people realize that it doesn't add much information. It's funny because as human you'd say, okay, color is a lot of information, is very important. The thing is, it's actually really rare that you have two colors which are different in color, but which are the same in black and white. It happens very rarely. If you see a black and white image, basically all the areas that have different color also have different gray values in the black and white image. So that's why the information gain for basically tripling the computational cost is not worth the effort. That's why few people do it, let's say. Okay, so just for time's sake, let's continue. This is the complete system. In order to navigate a quadrocopter, you need more than just visual tracking. You need more than just knowing the camera pose. You have the you also need to use the other sensors. So if visual tracking fails, you might want to use other sensors, IMU, altimeter, to still be able to not crash. And complete system, this all runs on the drone. Basically, it just sends out sensor data. Everything is sent to a laptop via wireless LAN, and then on the laptop, this is running. The monocular stamp system, which I just explained, which estimates the camera movement, it's undependable, it might fail. It has no scale information, basically a small world looks the same as a big world. And it has a large delay, so it takes roughly 250 milliseconds for an image to be captured, sent to the laptop, tracked, and then sent back to the drone. It takes a lot of time. 250 milliseconds actually is a lot of time in terms of quadrocopter flying. So what we do, these pose estimates are fed into an extended Kalman filter, which is a mathematical or robotical tool to fuse information from many different sensors. So for example, fuse the visual information with the IMU and the altimeter and so on. And it also is used to compensate for the time delays. So basically we have a model of the drone. We know that if it's in the air crooked, then it's probably going to flow to the left, right, whatever. We also know that if we send it a control command, fly to the left, it's going to fly to the left soon. So we can predict how it behaves and use that to compensate for the time delays. And we have a PID controller which then uses these estimated poses, which gets as input basically just I am here, and computes the corresponding control signal, which is then sent to the drone. Okay, so this is how the complete system looks like. Here you can see the drone flying, the AR drone flying completely autonomously, so I'm not controlling, I'm not doing anything. And it's just programmed to follow a given path. Camera view map, you can see the trajectory it thinks it took, and you can see how it can very accurately and very quickly fly from one position to another and then land again. What you can also do, you can tell it to keep a flying position, and then when there's some external disturbance like wind or me, it's going to fly back to where it's supposed to be. Here you can see what happens when visual tracking gets lost. Occasionally it's just going to try to fly back, visual tracking recovers, and then can actually fly back to where it was. So you can even see like it kind of drifts around, and then at some point visual tracking recovers and it can fly back. Here's what happens when I occlude cameras, altimeter, everything. It still works. It can still, like, using this visual information, it can find where it is, find where it's supposed to be, and then fly back to where it's supposed to be. Survives minor collisions. It's very handy. And so on. So this is basically what I'm going to show in, I guess, 10 minutes. Couple of words to the implementation of the software package. It's written in Rust, as I wrote. It's available as open source. So if you have an AR drone, if you have a laptop, if you want to play around with it, you're welcome to do so. It consists of 4 nodes, which are communicating. First and foremost, you have this GUI, which gives you the possibility, which allows you to send a flight plan or to construct a path consisting of waypoints and just send it to the drone, and the drone's going to fly this path. Might be anything. You get lots of information about the system, you get some messages, and most importantly, it has a backup joystick control, so there's a joystick connected to the laptop, and in case anything goes wrong, I can just immediately take over with manual control, which again is very important for developing, I guess. Second node does the drone communication, so that's the node that manages the Wi-Fi communication to the drone. Basically, everything that's sent from the drone to the computer is received by this node, and this node then again sends it out as ROS message, as ROS image message, ROS sensor message, anything. And this is then fed into the state estimation node, which does the visual SLAM, the visual pose estimation, the sensor fusion, and so on. Spits out the predicted pose of the drone, which is fed into the autopilot, which is the controller, which does the control. This autopilot node then sends back the control command to the drone communication node, which then sends it to the drone. So a very simple layout, is very handy, for example, that during development, if this crashes, you can still use the emergency control of the GUI because it's different processes, completely separated. If one fails, the other one still works. And this is basically, ROS makes it really, really easy to do this. A couple of implementation details. What we use in general in our chair. Said in the beginning, we don't really use Java that much. What we do use is MATLAB. I don't think many of you have heard of it. It's a very mathematical scripting language. It's really good to do, for example, to minimize a function, to do some algebra calculations and so on. You can just live code and see what comes out. Pretty much everything else is done in C++, because it's a lot of very mathematical stuff. So if you want to implement a formula, well, C++ just allows you to do it easily. And what we are very excited about, what we're doing in the last years a lot, is general purpose GPU programming. So that's leveraging the computational power of modern graphics cards to do numeric computations. On a modern GPU, desktop GPU, you have up to 1,500 cores, which can do numerical calculations in parallel. So that's really good for number crunching. Just to give you a couple of numbers, modern GPU has 2.1 teraflops, so 2.1 trillion computations, floating point operations per second. i7 CPU has 0.05, so that's about 40 times less. It's not that easy because it's very low level. You have many restrictions. Basically, this is only possible because a large part of these cores does the exactly same calculations on different data. You can't really, or you can basically do everything, but if you do it the wrong way, it gets really, really slow really quickly. And you have to worry a lot about things like no branching, because branching is bad. About coalesced memory access, so basically 2 cores which are in the same, or which are next to each other, let's say, have to access data in the memory, which is next to each other in the memory. Otherwise, it might get slow. For example, if all 1,500 cores want to write the same variable, then they have to do one after each other. So it takes 1,500 times longer than when they all write a different variable, because then they can do it in parallel. A lot of algorithms can be adapted to work on this 10 times, 100 times faster than on a CPU, but it's complicated. What we are very excited about is that currently there's a lot of development to bring this on mobile, so we want to have GPUs on mobile, which hopefully will be GPU compatible, so you can do this, you can leverage this computational powers on mobiles and maybe put it on a quadrocopter. Because putting graphics cards on quadrocopters is currently not possible because it's too big, it needs too much power. Okay, some examples just to give you an idea of what's actually going on. So this is a very simple function, it's a pixel interpolation. It just gives you the color of an image at any point in the image, let's say 5.3, 7.8. Bilinear interpolation between the pixel values. It's evaluated on my current project, which also runs in real time on the CPU, everything. It's called roughly 40 million times a second. So it's called often, really, really often. So it needs to be fast. Here's another typical function, typical thing. This is the error function I showed you earlier. In order to minimize it, you need to compute the gradient, which basically tells you in which direction you have to change C to get better. This is a small part of how you calculate the gradient. It's just mathematical formula plugged into C code. This loop, so this code part, again is evaluated about 50 million times a second. Because you have 30 frames a second, for each frame has 300,000 pixels. You need to do multiple iterations, so this runs often, and it runs a lot. You can actually make it 4 times faster if you use SIMD instructions, which is, I don't know, who knows what SIMD instructions are? Yeah, it's basically every modern CPU has it. It's a way of speeding up number crunching by basically doing the same mathematical operations you could usually do on one float on 4 floats simultaneously. So instead of adding one float to one other float, you add 4 floats to 4 other floats. So you do 4 times the work in the exact same time. Makes the whole thing 4 times faster. You can only do it if you need to do the exact same mathematical calculations on different data. And it gets very technical to implement. So basically you're down to assembler level. So you have a multiplication function which looks like this, and then you have to like extend this to look like really ugly spaghetti code. But it makes things 4 times faster. Okay, small outlook before I give the demo. Next steps, make it smaller, cheaper, and lighter. So we want to use smaller quadrocopters, we want to make cheap quadrocopters, and obviously they should be light. This is the Ladybug attached with a small camera. This is another quadrocopter which we use, which is even smaller. It's the Crazy Fly quadrocopter. We're currently working on putting a camera on this thing. So this is the idea. If you have something this size, you can just carry it around with you, throw it in the air, it can take a picture of you, fly back to you, you can catch it, and that's it. Obviously you can't really do any computations on board, so here definitely you have to just stream the video to maybe a smartphone or a laptop. The laptop does the computation, the tracking, and sends the information back. Second big step we want to take, make it dense. Currently, everything works on features, on these key points. This is basically how it looks like. Basically, the computer just sees the image at small spots, just sees small points of the image. This is bad if you want to do obstacle avoidance. This is bad if you want to do 3D reconstruction. We want to go here or even there, so we want to get dense. We want to get the depth of the image. We want to get to use all information that is in the image. So from this kind of really sparse dense map to this kind of semi-dense depth map, or even, I think on the beamer you can't see the colors very good, but this is a dense depth map or a roughly computed dense depth map of the scene. Obviously it gets computationally more expensive, but you have lots of advantages. You don't need to do all this feature matching and so on. This is an example where we use our big quadrocopter with a Kinect on top to make a three-dimensional reconstruction of our kitchen. It's flying around, and here you can see a three-dimensional model of the kitchen being built. It's a lab environment. The thing is tethered to the floor, so it can't fly away. Somebody's standing there with a remote control, backup remote control, but it's flying autonomously. And the idea is to basically use similar stuff in much larger environments to get real three-dimensional models of the world. And obviously make the quality of the model better. But still, something like this, if it's metrically correct, for an architect to have this of a complete, huge area is already highly useful to just see how it looks like, to measure stuff, to be able to plan stuff and so on. So you can see the poses of the quadrocopter, how it flew, and so on. So last but not least, this is my current work, how to do SLAM without key points, using gradient information wherever there is information in the image, and you get this kind of dense reconstruction which doesn't contain depth where there's no image information. If I have white surface, I can't say anything about what happens in the surface, but you can see I can get a pretty good three-dimensional model of the world. I don't save anything, so basically everything in the image after it leaves the image area is deleted, so I don't build a model, but still it's just one monocular camera. Actually it's a camera similar to this one, which is moved around the desk, and out of the movement of the camera, out of how the video behaves, you can get really accurate information about how this environment looks like. Okay, so we're at the point where I'm going to try to fly around. I hope it works. In the first row, maybe be careful. Yeah, it takes a while to boot up and connect and everything. Are there any questions meanwhile? So what I'm going to show you, basically the camera is pointing that way, and the quadrocopter or the AR drone is going to take off, fly a small rectangle, which I programmed in earlier, and then stay where it is.
I have a question actually.
Yeah.
Usually military is also very interested in this kind of thing.
Yeah.
And is usually quite advanced in that. Do you
Yeah.
have some ideas, or can you give something that leak through what they are thinking about, what to do with it, what can already be done with it, etc.?
Well, I don't think I know more than other people. Like everything I know from the press. What I do know is that, I mean, the military drones you hear of are different. They are big drones, they are fixed-wing airplanes, and they use GPS to fly around. They fly big distances, and well, I mean, they're made for different stuff. With a quadrocopter of this size, well, you can't really harm anybody. But yeah, I'm pretty sure that the military as well is interested in this kind of stuff and does stuff in this direction. Maybe if only to, I don't know, see or just see if there's something in the room where people are about to go into. With respect to quadrocopters, to be honest, I don't really know what they're up to right now. We don't have any affiliation with them, so I don't know. But I do know that a lot of this stuff is maybe not funded by the military, but at some point grew out of the military. So, for example, the complete ROS system, I said it was built by the guys who built Stanley from University of Stanford, in response to the DARPA challenge, which was this challenge to drive autonomously through the desert. And this DARPA challenge was issued by DARPA, and DARPA is the, I don't know what exactly it stands for, but it's like the Experimental Research Institution of the US military. So they are the guys who invented this challenge, they are the guys who put out the $2 million reward, and then people from Stanford came and say, hey, I want to participate, I want to do this here. See? So even the whole ROS system kind of has a connection to the military. It doesn't have any connection at the moment, like ROS is run by Open Software Foundation, not by US military, but I mean even the internet came out of military in the beginning, so yeah. Yeah?
When you were, like the other question, that other drones are using GPS.
Yeah.
So why not use GPS to augment like rough positioning for the quadrocopters? And second question goes to the other direction. You said that you use the IMU for also for like fallback positioning, but do you also use it when you have the visual positioning recognition as to augment this in a, like, I don't know, second order approximation?
Yes.
Also?
Yeah, so the IMU is always used. It's always used to smooth the trajectory, but in fact it turns out that when you have visual information it's so much more accurate than the IMU. Basically the IMU doesn't have any votes left. But it's heavily used to fill this 200 millisecond gap between last visual information and current state of the drone. So the IMU is always used, but it's a lot less accurate than the image information. And to your second question, I mean, this drone doesn't have a GPS on there, so we can't use it. But in general, GPS is not available in buildings, and it might be unreliable. So yes, whenever it's available, it adds a lot of information and it makes things a lot easier. But we're from the computer vision chair, so our goal is to see how far we can get with cameras. And ultimately, you have to be able to do all the navigation stuff without GPS, because in a building you don't have GPS, in like between two buildings on the street you might not have GPS. GPS is very inaccurate, so we want to focus on what you can do without GPS. I mean, obviously most of the drones who can fly autonomously now all use GPS. They can all only fly up in the air, very high up, where there is GPS, but they can't fly below a bridge, for example.
And when you, I mean, you don't need a computer for steering, or?
Yeah, now it all depends on the computer, because the Yaodron doesn't have much of a computer on there.
Also used, or that's also used when you do like formation flight, the videos you were showing before?
In the video you had an external tracking system and several external computers doing all the control stuff.
So like for formation flight, could the positioning or relative positioning at least be augmented by like, if you have like 16 of these things, they help each other?
It's possible, probably.
Not like current development.
Yes, there are people working on that. So there are people working on that to get like swarm flight to one drone sees the other drone and tells the other drone, hey, you're actually there, for example. There are definitely people who work on that. I mean, there's lots of possibilities.
Yeah, there is a video where a flying drone controls robots on the ground.
Yeah.
It goes by blinking lights, and then it recognizes which robot is which, and then it sends controls to the other.
Yeah.
I got a question.
Yeah.
Relating to the visual information, I assume you already, are into the new tech stacks of the new Kinect, which is not dependent on the light circumstances anymore.
You mean the Kinect 2?
Exactly.
Well, we don't have it yet. I think nobody really does. Yeah. But the thing is, personally, I'm more interested in what you can do with just a camera, because the Kinect has limited range, for instance. But then again, yeah, the new Kinect is better than the old one, obviously.
Well, thank you for the information. The second question would be, well, I'm into combining technologies. Did you ever think about using your technology and for showing off and controlling purposes, combined with the Oculus Rift, which would give you quite a very interesting experience?
Yeah. Well, we actually have like something similar to the Oculus Rift, like an old version where you have the remote control which you can like measure, like move around, and then a ground station which measures the position of this remote control, and you can just like get the position. So it's kind of Oculus Rift, but without just fingers. But yeah, would be cool. I mean, first experiments towards that, you could see the key neck tracking of a person who could like control the quadrocopter like this. We're not working on that currently, but yeah, it would be cool. Definitely. Yeah.
How tall does your computer need to be? Can you do the controlling with your smartphone, or?
With this smartphone, no. With a really, really modern smartphone, yes, I guess it would be possible, but you'd have to implement it. Actually, this laptop is way too powerful for this stuff. It just, right now it runs on any decent, not older than 2 years old hardware. But I mean, you can scale it up and down, and it runs better if it has more computational capabilities. Yeah.
Just another question referring to the GPU power you were talking about earlier. I guess you also took into consideration the Tegra chipsets, which are like super powerful GPUs for mobile phones, NVIDIA.
Yeah, we don't have anything with GPU on mobiles yet. We're just using the desktop mobiles. And there, the numbers I gave you are from the Kepler Quadro K5000, I think. But we're not working on mobiles yet. But it's thinkable, let's say. I mean, the cool thing about a mobile is basically it has a lot of sensors. It's really comparatively cheap. It's light. You can stick it on a quadrocopter, and then it could serve as like computation hub or sensor hub and stuff like that. I mean, basically, the idea is to use hardware that's sold millions of times for other purposes and use it for our purpose, just because it's not because it's made for that, but because it can be used for that. Yeah. Okay, so just let me show the demo before I answer any more questions. Just a quick check. Yep, it does actually work. So here you can see the live view from the quadrocopter. You can see the map. And now I just started it. Flies up, makes the initial map. Flies up and down mainly to get the scaling right. And now you can see visual tracking is lost, but it can still do a little bit. Okay, it's supposed to fly a small rectangle, which is not too accurate. Okay, let me just restart it. So please just delete the video and make me one. Yeah, I mean, I said it might fail. Again, initial map. Also, it might be a problem that I'm standing in the image, so if I move too much, probably not good. Okay. So now it works somewhat better. Just for demonstration, fly for a small small rectangle. You can see path it takes here. You can see all those dots, which are the well points, which are the points recognized here. And the path it thinks it took. And now it just flies back to its origin and stays there. So what I can do now is semi-interactive control. I can tell it to fly 1 meter up. It's going to fly 1 meter up. I can tell it to fly 1 meter to the right, so towards you guys. And it's going to fly 1 meter there. or 1 meter 80 to the left, by 1 meter 80 to the left. So this is a lot easier to control than with the control stick. What I can do now is the pushing away part. So it's programmed to stay where it's supposed to be, and if I push it away, it slides back. You can see there's a small delay, so I push it away and it takes a small bit of time before it reacts. That's these 200 milliseconds delay, which you can remove if you do all the computations onboard. If you do them all offboard, then well, you have to deal with it. Extreme case, rotate, visual tracking is lost, visual tracking recovers, and it slides back. So again, rotation. And you can even see, like when I rotate it and push it away very far, how it first rotates back, visual tracking recovers, and then it can slide back to its original position. So if I do this, rotates back, refines position, and slides back. That's simply because without the visual tracking, it thinks it's at the correct position, but it actually isn't. Visual tracking recovers, can correct it to its pose estimate, and then slide back. All I can also do is, like, if I occlude this camera, you can see that it starts drifting around a little bit. So over time, it's not going to be able to hold its position very accurately. If maybe I push a little bit now, it gets lost, and only when visual tracking recovers it can really slide back to its original position. So very extreme case, including everything. Now basically it doesn't know where it is. Right? Can't do anything. Come and recover, it can find back. Okay.